Hey there, Ken the Metal Professor here. It's time for me to work through some Calculus 1 type problems. Last semester, I started out really well at the beginning in trying to post videos fairly regularly, mostly by poking around online and see what questions people were asking about things, or just posting something that I thought was kind of fun to talk about. I lost my mojo. And this semester I'm going to try again and see what we can do. And what I thought I would do is pick some online problem sets using the platform WebWork. If you haven't used it, it's very much like WebAssign, was the Pearson My Math Lab, where you can enter expressions as answers for questions and they will be scored immediately. And so we can get that warm fuzzy feeling of getting the green instead of the red on the screen when we get correct answers. It helps me organize the problems I'm going to want to do. And I'm going to try to select problems, if I don't lose my mojo, that sort of follow along a pattern of problems that folks might be working on in a Calculus 1 or Calc 2 or Calc 3 setting. And I'll also dive into Reddit, and if there's any interesting questions, maybe do a quick video based on those. But today I'm just going to run through some problem solving involving limits, because students in Calc 1 will be encountering them fairly soon, if not already. And so you can see on the screen a limit problem, which we're going to talk about first. And this is just a graphical limit problem where there's a graph, on the screen. There's little ticks and dashed lines to give us markers on the X and Y axis, and a whole bunch of values that we're supposed to put in there about the function that's shown in green. So the first row, part A of this question, this looks like a ton of work to do, but it isn't really, because we're just going to be picking values off the graph. The first row is investigating values of the limit of this function in green here as we approach -1. You probably can't see the fine tuning here, because it gets, first of all, it's a subscript, and then in that subscript there are superscripts and that are kind of hard to see. So with my, whoops, wrong click, with my bad handwriting, I've put up here some of the values that are requested, and I've emphasized the fact that when we are looking for the limit of this function, limit of f of x, as x approaches -1, there's a little bit of an extra bit, -1 with a minus sign up there in the corner, -1 with the positive sign up there in the corner, and those tell us whether we want the limit of this function as we're approaching from the left, from negative x values, or from the right, positive x values. And I honestly don't know if I'm pointing in the right directions based on what happens with the camera, and it might turn things around. But when we get to the graph, we will be able to take a look. So let's go investigate limits around x equals -1. So here is -1 on the graph, and it looks like the function follows along a ramp and then a flat line. X equals -1 provides what would be the connection point. Now this function has a hole in the graph, and a value for the function is up there. That's okay. Limits worry about what's happening as we get closer and closer to a particular x value. They don't care what happens at the x value. So when we are asking for the limit as x approaches -1 from the left, we are in a little calcmobile, and we are on the x-axis, and we are approaching -1 from the left of -1, and we're asking, what does it look like the function is going to hit when we get to x equals -1? Well, if we're riding along on the axis from the left of -1 and approaching -1, on the graph we're going up this slope, and by golly, it sure looks like by the time we get to x equals -1, we should hit a value of +1 for the function. Now, because we see this green dot, we know that the function doesn't actually hit y equals 1, but we don't care when we're talking about limits. So as we approach -1 from the left, it sure looks like the function is about to hit +1. Similarly, if we're in the calcmobile and we're driving to -1 from the right, we're riding along up here on the function for our y values, and all those y values are +1. And so our prediction would be that by the time we get to x equals -1, we're probably going to hit a y value of +1. And so if I go back here to my sheet, I would say that both of those limit values are 1. And the third question is asking, what is the overall limit of this function as x approaches -1? What that does is it compares the limit from the left and the limit from the right and compares them. If they're the same thing, then the overall limit exists. As we approach -1, as x approaches -1 for this function, from both what just happened? From both directions, it sure looks like one's coming up the slope, one's flat. It sure looks like that our two directional approaches to x equals -1 are both going to collide at that y value of 1. And so the overall limit, since approaching from the left gives us a limit of 1, approaching from the right gives us a limit of 1, we would say that the overall limit is equal to 1. Now, the value of the function at x equals -1 doesn't care what those limits are. And in fact, we see that based on the graph, the actual y-coordinate or functional value for this function at x equals -1 is +2. Right? Again, the information in the blue box doesn't care about the 3 entries above. The limits don't really care about the value of the function at the target point. And the value of the function at the target point doesn't necessarily care about what it looks like we were approaching as we get there. Now, good stuff happens when these things match up, and that's a concept called continuity, but that's a little bit later down the line. Okay, row B here poses exactly the same train of thought for approaching +1 from the left, from the right, and overall. So here's x equals +1. As we're approaching from the left, we're on this flat portion of the graph. So if we were gambling people and we had to make a wager as to what we were going to hit when we finally got to x equals 1 as we were approaching from the left, we would wager, boy, it sure looks like we're going to hit y equals 1. Flip to the other side. Now we're approaching x equals 1 from the right. So we're coming into x equals 1 on the x-axis, which means we're riding uphill on the graph of the function. And so from the right, our wager would be, boy, it sure looks like we're going to hit y equals 2 by the time we get to x equals 1. Okay? And then the overall limit here does not exist because from one direction we think the limit is 1, from the other direction we think the limit is 2. Which one's the limit? Well, neither, because they don't agree. The value of the function at 1 does exist. We just look for the closed dot instead of the open dot, and that would be 2. And then in the third row of the expected responses, all the same business except at x equals +3, which is at 1, 2, 3. Here's x equals 3, and down here, as we approach x equals -3, as we approach x equals +3 from the left, on the x-axis, we're actually riding down the function. It sure looks like we would be hitting y equals -3. As our x values approach 3 from the right, we are riding along this little bitty sloped part of the function. And again, it sure looks like that the y value we're approaching is -3. So in this case, the two limit values from the left and from the right are both -3. That means the overall limit does exist and is -3. What is the value of the function at -3? Well, I'm looking for it. There isn't one. That's okay, because again, the value of the function doesn't care about the limits and vice versa. And heck, we don't even have to have a value at 3, and we don't. And so that box would have to be left empty. So just to get that Pavlovian response when we see that all our answers are correct, I'll put these in again. As we approach -1 from the left, the limit was 1. From the right, it was 1. So the overall limit as x approached -1 was 1, but the value of the function was 2. And then as we approach +1 from the left, limit is 1. From the right, the limit was 2. That means the overall limit does not exist. And the instructions tell us to enter DNE. And then for that case, and then the value of the function at 1 is 3. Whoops. And now see, I got rid of the big version of this picture. I've got to change these values. The limit from the left was 1. Nope, that was correct. 1, 2, and yeah, the value of the function is 2. That's what I was messing up here. And then for x equals, for the limit as x approaches 3, from the left, the limit value is -3. From the right, the limit value is -3. And at x equals 3 itself, is there a value of the function? There is not. It does not exist. Whoops, wrong box again. Dang it. And I skipped all over the limit value overall as x approaches 3. That's going to be -3. Check my answers. Oh, the green is outside of your view. So sorry about that, but at the bottom at least you can see all of the above answers are correct. On my screen, there's a huge row of green boxes for every one of those entries, just says correct. So it's a swath of green from the top to the bottom. And that makes you feel good when you've spent time answering all these questions. Okay, so there were some examples of just a graphical limit problem. And let me take a quick pause and pull up one that's a little bit more calculation based. Okay, here's a problem that's a little bit more calculation based, but it's a very simple one. I'm not going to stress myself or you too much on this initial set of problems. It's asking for the limit as x approaches 2 of the function 3x over 5 plus x cubed. The way we evaluate limits like this is to start with, in our train of thought of how we might approach this problem, is the theory of don't make it harder than it needs to be. Informally, the way we can put this is that if you can take the limit point, plug it into your function, and get a number back, chances are that's going to be the value of the limit. There are more formal ways to say that. Those can be found in your textbook, I'm sure. But in a practical sense, as we're looking at the limit as x approaches 2, let's plug 2 into this function and see if anything wacky happens. And if not, that's probably going to be the limit value. Now, you looking at this function, there is a denominator that has a variable, and you might say, uh-oh, what if we are near the place where that denominator might hit 0? Well, since the denominator is 5 plus x cubed, that would hit 0 at x equals cube root of -5, or negative cube root of 5, either way, and that's not anywhere close to 2. So, well, the cube root of 5 might be close to 2, but it isn't 2. That's the point. Okay, so, yeah, let's just plug in 2 and see what we get. So I'm going to just take this function. I'm going to call it f, and I'm going to plug in 2. And we're going to get 3 times 2 over 5 plus 2 cubed. And that's just going to be 6 over 5 plus 2 cubed is 8, so 6/13. And that's not going to simplify any further. So for this particular function, there is an asymptote in the graph of this, but it's not going to happen at x equals 2. There will be no other shenanigans. So going with that informal rule of if the function behaves at 2, that's probably the limit value. Let's just go with it. So I'm going to come back here and I'm going to plug in 6/13 and check my answer. And again, I think I'll see green. Yep, it's outside your window again, but you can see this thin bar of green here. The above answer is correct. Okay, a last example here. I already tried to start this once, and as soon as I did, somebody walked in front of the house with their dog, which made my dog start barking. So I paused, and here we go again. Let's hope for the best. This involves finding a limit value for a larger function, which is built of a couple of individual functions, and we actually don't know what those functions are, but we do know both of their limits as x approaches 4. So the limit as x approaches 4 of the function f is 3, and the limit as x approaches 4 of the function g is 6, and now we are going to look for the limit as x approaches 4 of the bigger function, which is f plus g over 5 times x. There are going to be a ton of limit laws that you're going to come across in your study, in your textbook, in your class notes, which are going to tell you basically what ought to be fairly reasonable anyway, that the limit of a sum of two functions is going to be the sum of the limits of those two functions at the point of interest. The limit of a product of two functions is going to be the product of the limits of those two functions. And the limit of a quotient of those two functions will be the quotient of the limits as long as the limit that's going into the denominator isn't 0. And while I've been talking, a car has parked in front of our house. The neighbors have come home. I'm going to pause in case the dog starts barking again. Okay, my dog doesn't care if it's just a person. She only cares if it's another dog, apparently. All right, so we are looking for the limit as x approaches 4 of the function built as f plus g over 5 times f. And so you would hope that the following works. That the limit as x approaches 4 of this larger function built of the smaller is just going to be the limit of f plus the limit of g in the numerator over the limit of 5 times f in the denominator. And that's exactly how it works, right? The limit law, this is one of those rare cases where math actually works the way you hope it would, and it doesn't get complicated just for the sake of getting complicated, right? And so these are the limit values that we are given in this problem. We are told that the limit as x approaches 4 of f is 3 and g is heading for 6. And so in this work, we know that this limit value is 3. We know that this limit value is 6. I had to check. And now down here on the bottom, there is an extra limit law that I haven't put in place here because I just wanted to emphasize that the limit as x approaches 4 is basically the limit of the numerator over the limit of the denominator, as long as the limit of the denominator isn't 0. And then the limit of the sum in the numerator is just the sum of the two individual limits. There's multiple limit laws in action here. I'm not stating them formally, we're just kind of following our nose. Down here, the limit of 5 times f of x, you would hope would be 5 times the limit of f of x as we approach 4, and that is in fact how it works. And so down here, we can just put 5 times the limit of f, which we know was 3, and altogether then this result will be 9 over 15, which would reduce to what, 3/5? So I'm going to close this down. I'm going to put it, you know what I'm going to do just to show off? I'm going to put in 9/15 for this. I'm going to check the answer. We should get green. Yay, we got green. WebWork understands equivalent values. So simplified, the answer ought to have been 3/5. And in fact, if I go back and make that 3/5 and try it again, it's still correct, right? So that's how that little combination of individual limits gets put together into that one. It would be more interesting if the limit of the denominator went to 0, because then in order to have an overall limit, something would have to happen in the numerator to sort of balance that out, and that's a whole other thing. Maybe that's a sample problem that I'll pull up next time. So I hope a little bit of review of limits helped you out in your own problem solving, and yeah, that's all for now.